Okay, hello everyone, welcome to Vibrations in Acoustics. I'm going to go over how to solve an ODE, particularly one that is set to some trigonometric function like sine or cosine, because that's what we'll normally deal with in vibrations. So this is going to be a purely lecture video. I'm going to go through, do it symbolically, and basically derive a huge number of important values and equations that you need to know in case you haven't been presented with them before. Okay, so solving an ODE. Once you have a typical ODE, you need to make sure you note the constants, they're the coefficients of each part of this. So the omega, A, B, and C. So, and then you go ahead and you can jump into the characteristic equation. Or, yeah, the initial characteristic equation, which is going to be A lambda squared plus B lambda plus C equal to 0. When you're first starting out, you always set it equal to 0, ignore this part, and then you find the homogeneous solution based on the roots and this kind of thing. So this is the characteristic equation. Okay, from there you find the roots, which is lambda 1 and 2, which you can, if you can't factor it right off the bat, you can always do minus b plus or minus square root of b squared minus 4ac, the quadratic equation, all over 2a. If you get anything more complicated than this isn't going to really happen, but in this vibrations that I'm doing for most of these videos, it's going to be linear systems working with trigonometric solutions and that kind of stuff. So it's not going to get too darn complicated, and the weird sideways stuff you can do in a differential equations class. Okay, so now, once you get the roots from the characteristic equation, what you have to do is you got to see if there's a couple conditions that you have to meet. So if you get two real roots, so basically no i's or j's stuck in it, so, and lambda 1 does not equal lambda 2. They're distinct, two real distinct roots. Or B, if you get two real identical roots, where lambda 1 does equal lambda 2, and this would be like both of them equal to a number like 2 or something like that. Oops, sorry. Would have been better if you guys could see that. So lambda 1, lambda 2. If they're not distinct, then you have lambda 1 is equal to 1 and lambda 2 is equal to 2 or something like that. So pretty basic. And then the third condition or situation is two complex conjugates. Basically alpha plus or minus beta j. So you have a real part and an imaginary part. This is where it starts to get kind of hairy. So if you go ahead and look at these two conditions, there's some basic equations you can get out for the homogeneous solution. So for the homogeneous solution, this solution is totally based off of what these roots are. So if you have condition A, the kind of equation you'll get is C1 e lambda 1 t plus C2 e lambda 2 t. So you set in some coefficient of C1 and C2, and you align it e to the lambda, whatever the root is, times t. And you just go on like that. If you have more roots, then you would add in C3 e lambda 3t, and so on and so forth. If you have the second condition where they're both real and identical, then you have C1 plus C2 times t e to the lambda t, where lambda is the root, in this case like 2, and then you have C1 plus C2t. The t is basically dependent on multiplicity. Up here, the topic of multiplicity, right here you have a multiplicity of 2, not because of this value of 2. I'm going to actually change this value. These are equal to 3. You have a multiplicity of 3 because you have two roots equal to 2. So if you have a multiplicity like that, then you have an extra t added on for each extra root that you have on. So if you were to have like a multiplicity of 3, then you had C1 plus C2t plus C3t squared times e lambda t. Now there's also the condition, this is for the multiplicity of 2, so if you have like 3 roots, let's say we have roots of 2, 2, and 3. These are the 3 roots going into here. you have a multiplicity of 2, so you get this first part, and then you go on to plus C3 e to the lambda t. So that's how you kind of graph these two situations together. You have a multiplicity of 2, so you add in this little coefficient with a t on it, but then you also have one extra root where you add on another coefficient and the normal setup without the addition before. Hopefully that's clear. Okay, and in the third condition, C, and it's totally in a league by its own, e to the alpha t of C1 e to the j beta t plus C2 e to the negative j beta t. And right here, if you have two complex conjugates, plus or minus, you take the alpha to the outside, the real part to the outside, you use the two coefficients, and then you have the beta for the plus and the beta for the negative. And there's no multiplicity here because they're distinct, so there's no extra t added on anywhere, you just add those up. So that's the three conditions you can have. And from these are basically your homogeneous solutions, any one of these equations, based on what your roots were. Okay, then you have the particular solution. Particular solution. This is where you actually deal with this sign up here. So going ahead and working on this now. Let's see here. Particular solution. The way to get this is we have an equation, g of t, which I'm going to represent the a dot, so on and so forth stuff. So we've got a dot g of t, which is equal to a sine of omega t. Okay, let me move something here. This is also equal to the imaginary part. The reason I'm bringing this up is for the people in vibrations. This is a vibrations course, t. So the imaginary part of this, which because this part is normally equal to cosine of omega t plus j sine of omega t. That's what the ae j omega t is. You can do a direct conversion between these two functions because they're related, and that I show in a different video. But this is the real part, this is the imaginary part. Imaginary part, real part. Since we have a sign over here, you automatically go to the imaginary part, hence this notation. Okay, so, but we don't want to deal with just the imaginary part, we need this full function. So what we're going to do is take this down here, we're going to set xp, the particular solution, equal to some coefficient times cosine of omega t plus j sine of omega t. But that's kind of nasty, especially for this problem, so we're just going to simplify it to c e j omega t. Like I said, these directly convert, so we can take this part, stick it right on over here. So now we have a particular solution set up. If that's our particular solution, we should be able to substitute it back in for x into the differential equation back up here, taking the derivative as we go along. So, taking this value and putting it back up here into this differential equation, this is going to be a long derivation, so get ready. A of negative omega squared times c e j omega t. Plus b of j omega times c e j omega t plus c of c e j omega t is equal to a e j omega t. So this is the full particular solution. What I did in each one of these parts was I took the derivative of this twice for this, took the derivative of this once to get this, and didn't take the derivative at all, just substituted it straight in for this, into this differential equation up here, because this was x double dot. So if you're confused, just go ahead and do that derivative sideways. I skipped a step because this is going to be long enough as it is. Okay, looking at that then, we know that we can cancel all the e, j, omega t's, and now we have c of negative a omega squared plus j b omega plus c is equal to a. So we have all of these values except for the c value, because up here in this equation we had all these coefficients in a and omega t. So we have all these values, so we need to solve for c. So c is equal to a all over negative a omega squared plus c plus j b omega. Okay, so then we want to kind of clean this up a little bit. So what I'm going to do is I'm going to take C is equal to A all over C minus A omega squared, which you can kind of consider by itself, plus J B omega. And I don't want this imaginary part in the bottom, so what I'm going to do is I'm going to multiply this by 1. C minus A omega squared minus J B omega all over C minus A omega squared minus G B omega. Which yields A of C minus A omega squared minus A J B omega all over, wow, this just keeps on going, doesn't it? C minus A omega squared plus B squared omega squared, all which we're going to call this piece B for right now, just as a placeholder because there's a lot of stuff to write. But this is also useful too because these are basically sides of a triangle, and I mentioned this in other videos, but this is based off of the imaginary parts of a triangle. So if you're looking at this like this, and this is the imaginary plane, and this is the real plane, you've got C minus A omega squared plus B omega over here because this is the imaginary part, and this is the real part. So that's what B is. B is basically the hypotenuse, which is all of these squared or the square root of them. So kind of a side topic, but anyway, moving on. So then C is equal to A over B times C minus A omega squared minus JB omega. Okay, so now we have C. So we can substitute that back into the particular solution at the top, and we get xp of t is equal to A over B of C minus A omega squared minus GB omega, close that up, times cosine of omega t plus J sine omega t. Okay, I made kind of a leap again, but we solved for C. So you can take this all the way back up here. I know we did it in respect to this right here for a minute, but you get to take it all the way back to this point and substitute C into this equation, which is what we got. Now this is weird because we've been jumping between these two notations, but this notation is easier to take the derivative of, so we solved for C using this equation. You could have done it with cosine too, but it just would have been more derivations. But once you get C, you can take it all the way back into this format. So that's why we just made that leap. Okay, so then expanding this further and multiplying this out, this is equal to A over B times C minus A omega squared cosine of omega t plus B omega sine of omega t. What I'm doing is I'm basically separating the real from the imaginary, plus J of A over B times C minus A omega squared sine of omega t minus B omega cosine of omega t. Okay, so kind of scrunched up, but omega t right there. So now, since g of t is equal to the imaginary part of a e j omega t, because we're equal to sine, which is the imaginary part of this, but we've been solving it as if we have the entire part of it because it's easier in the notation. Since we only need the imaginary part, we can basically kill this whole real part right here. So then xp of t, which is equal to the imaginary part of this, is then equal to A over B times C minus A omega squared times sine of omega t minus B omega cosine of omega t. All right, so The j dropped off because j just basically denotes that it's imaginary. So we took this whole piece and we set it equal to xp because it's imaginary. So then we can simplify this a little bit more. Xp of t is equal to ap of sine omega t plus alpha. So we know xp is equal to that because we have this up here. We're jumping back and forth a lot, and I apologize for that, but that's how you have to solve these problems. It's constantly playing with the numbers and moving in with what you can and slowly moving back to what you want. So this is the base fundamental equation that this represents. It's going to be equal to this, basically. So, in order to solve this, get a new sheet of paper here, solve this mess, AP is equal to A over B square root of C minus A omega squared plus B omega squared. Alrighty. Again, that was a leap. This is actually from a previous video, and it's really similar to what I was talking about up here, of A being the amplitude of C. B is this value. A is actually the hypotenuse of this. So let me rework this. If you're looking at an imaginary plane, and this was initially imaginary earlier in the problem, these coefficients, you're looking in the imaginary plane, and you've got an angle alpha right here, and you've got C minus A alpha squared right here, and B omega right here. These are the two sides of the triangle. If you square them and then take the square root, you'll get A, which is the amplitude. That's where that comes from, which is a very abstract thing, but it comes from earlier when you're looking basically at this equation. And you can relate this A. So like if you took this, multiplied this by C, A, you get equal, that would equal A, and so on and so forth. Or this part, I guess. But it's very abstract, and that's a whole nother differentiation proving this equation, basically. But you can also look at it at this equation right here, too, of sine and cosine. This is basically a trig identity of sine minus cosine. So you can pull out this value right here, square it, pull out this value right here, square it. These are the two sides of the triangle. When you're multiplying by sine and omega sine, you get the hypotenuse. And then you have this coefficient out in front, which is where this comes from. So that's a couple, 3 different ways of looking at it. If you really want to simplify it down, you can just say, pluck this value from in front of the sine and this value from in front of the cosine. Cosine is related to a j opposite. In this case, B right there, cosine right there is right here. So that's how you can kind of look at that. Hopefully that makes sense, helps you out a little bit. So then alpha is equal to negative A tan, the arctangent, of B omega over C minus A omega squared. Just like that. And this is obvious because if you got these two sides of the triangle, then SOHCAHTOA, opposite over adjacent, inverse tangent gives you the angle. Okay. So now you have your particular solution. Xp of t is equal to A over square root of B sine of omega t minus A tan of B omega all over C minus A omega squared. This is for an imaginary. If you were in the real, then it'd be A over square root of B cosine of blah in here. Whatever this stuff is. Oops, sorry. So, that should pretty much cover it all. If you're thinking of where the square root of B comes from, it comes from this equation, kind of solving it out again. It's a lot of weird leaps, I understand, but hopefully it's a little bit clearer than what you've had before. Okay. Let me check something real quick. Okay. So on and so forth. That's good right there. That's good right there. Yes, this whole equation comes from this chunk right up here, where you take the square root of b, take the square root of all that stuff, and sub it in for the sine, basically. Okay, so hopefully that's what your equation is, and to get the final solution, you take the x homogeneous t plus xp of t. So you get xp right here. This is based on imaginary or real. Now that we've derived all this, you can basically just skip to this step, pulling out whichever equation you want based on what the solution given at the beginning of the problem is. So since it was sine, you're like, this is the imaginary part. I can pluck out A, B, C, big A, omega, plug them into this equation, or this equation, or this equation based on if it's sine or cosine, and you've got your particular solution. So that's how a vibrational ODE is solved.